Swayam Prabha. Digital India. Educated India.
We continue our discussion of the solution of the diffusion equation. We were looking at solutions in the spherical coordinate system. Okay. I had derived solutions for you by separation of variables, and we got this rather complicated form, okay, for the temperature field. Okay. It was basically a spherical harmonic expansion where y and m of theta phi were the spherical harmonics, and that was multiplied by two terms, one of which was increasing as r increased, the other was decreasing as r increased. Okay. One was increasing proportional to r power n, the other was decreasing proportional to 1 over r power n plus 1. Okay. We had also solved the same equation in a different way, okay, and that was to consider the delta function solution, okay, to consider an inhomogeneous term in the form of a delta function. Okay. And for that we had got the solution as q by 4 pi k times the distance between the source and the observation point. And in the last lecture we were trying to see what it is that the relationship between these two kinds of solutions. Okay. You have one solution wherein you express the inhomogeneous term as a source term, okay, and then you get the temperature field. The other is this expansion, okay, a times r power n and bn by r power n plus 1. So, for n is equal to 0, I told you it is a point source. Okay. We had already solved the equation for a point source. You just get q by 4 pi k r. That is the exact solution that you get by solving this as well for a point source, a delta function source. Okay. What do the other terms in this expansion mean? So, for this let us take a source, okay, plus q, okay, at a location, okay, L by 2, okay, along the z axis, okay, and then take a sink, okay, minus q at the location minus L by 2. Okay. So, we have a combination of a source and a sink which are separated by a distance L along the z direction. What is the result for the temperature field that I would get for this configuration? Okay. We had actually solved this. Okay. What we need to do, okay, is to take a source and a sink and just superpose the temperature due to each one of them individually. In this configuration, since I have a combination of a source and a sink, the flux lines will be parallel, perpendicular to the mid plane between those two. Okay. So, therefore, the temperature is equal to q by 4 pi k into the distance, okay, between the any point, okay, observation point x, y, z, okay, and the source location. Okay. The source location, okay, x s is at 0 0 L by 2. Okay. It's along the z axis. So, the x and y coordinates are 0 and the z coordinate is at plus L by 2. Okay. The image of the source is at 0 0 minus L by 2, that is the sink. So, this is going to be equal to x square plus y square plus z minus L by 2 the whole square root of. Okay. So, that is going to be equal to the temperature due to the presence of the source. Okay. The sink has strength minus q. Okay. So, the second term in this will be equal to minus q by 4 pi k into x square plus y square plus z plus L by 2 the whole square, whole to the half. Okay. And that is because the sink location is at z is equal to minus L by 2. Okay. So, z minus the sink location is going to be equal to z plus L by 2. Okay. Now, what happens if the distance from the source or the sink is much larger than the separation between these two? Okay. In other words, what happens for r much greater than L? The distance from the source or the sink is much larger than the separation between these two. Okay. So, what you can do is to expand this temperature field. Okay. So, I can write this as x square plus y square plus z square. Okay. Okay. I will get minus z L, okay, plus L square by 4 whole to the half. Okay. Just expanding out this z minus L by 2 the whole square, and I will get the second term as minus q by 4 pi k into plus z L, okay, plus L square by 4 whole to the half. Now, we use the substitution that x square plus y square plus z square is equal to r square. Okay. That is the distance from the origin. So, this I will get q by 4 pi k into r square minus z L plus L square by 4 whole to the half. Okay. Now, I take r out as a common factor in the denominator in both of these expressions. Okay. You take r out as a common factor in both of the denominators. So, I will get q by 4 pi k into 1 over r into 1 minus z L by r square plus L square by 4 whole to the half. Minus 1 over and now, since r is much larger than L, I can use an expansion in L over r. Okay. I can use a binomial expansion in L over r and just retain the first terms in the series. Okay. 1 over r into 1 plus z L, sorry, okay, just retaining the first term in the expansion. Okay. 1 by 1 minus x to the half is 1 minus half x, 1 by 1 minus x to the half as x goes to 0 is 1 plus half x. Okay. Then I have the second term here, which is 1 over r into 1 minus 1 by 2 z L by r square. Okay. So, this is effectively equal to q by 4 pi k r into z L by r square. Okay. So, let us look at what this means. Okay. So, I had started off with a problem with a source plus q, a sink minus q, separated by a distance L, okay, and I was trying to find out what was the temperature at some location T of x, y, z. Okay. For the case where this distance r is much larger than L. Okay. And retaining just the first term in the expansion, what I got was T is equal to q by 4 pi k into r into ZL by r square. Okay. I can write this as q by 4 pi k, okay, into L, okay, into Z by r cubed. Okay. Since Z is equal to r cos theta, okay, if you recall when we did a spherical coordinate system, Z was equal to r cos theta. This is equal to QL by 4 pi k, okay, into cos theta by r square. And since when we do the expansion in the Legendre polynomial series, okay, we know that this is also equal to QL by 4 pi k into P1 of cos theta by r square. Okay. Let us refer back to the expression for the temperature that we had derived earlier. Okay. For m is equal to 0, y n m of cos theta was just equal to y, okay, and 0 of cos theta. Okay. So, therefore, if you take this expression and take the value for n is equal to 1, okay, for n is equal to 1 and m is equal to 0, okay, the temperature becomes A1 r plus V1 by r square, okay, into P1 of cos theta. I am sorry, yeah, okay. This term here 1 over r square times P1 of cos theta is exactly what I have got over here. Okay. So, therefore, the superposition of a source and a sink separated along the z axis gives me the solution for n is equal to 0 and n is equal to 1 and m is equal to 0. Okay. This is called a dipole, okay, a point dipole. In the limit as L goes to 0, the separation of the source and the sink goes to 0. In the limit as L goes to 0, while Q times L is finite, okay, as you make the source and sink closer and closer to each other, while retaining Q times L to be a finite number, you get a point dipole. Solution for the point dipole, the temperature decreases as 1 over r square. I have a source and a sink close to each other. That means that outside of these, there is no net source, because whatever is coming out of one source is going back into the sink. There is no net generation of energy. The net source is equal to 0. For a point source, I had told you that the temperature decreases as 1 over r. In this case, there is no net source. You have a superposition of a source and a sink such that the net energy from one goes back into the other. There is no net generation of energy. In that case, the temperature decreases as 1 over r square. Okay. So, this is the dipole, okay, the point dipole, okay, with a dipole strength which is given by Q times L. Okay. And the combination of these, if you plot, okay, if you plot a source and a sink close to each other, the combination of these is going to give you flux lines that start from one and go to the other. Okay. This is the dipole solution for the Laplace equation. Okay. These are the decreasing harmonics, okay, the decreasing dipole solutions. Okay. that decreases as 1 over r square. Okay. There is a second term that increases proportional to r, okay, that instead of having 2 points close to each other, if you have a source and a sink, okay, far from each other, the flux lines will look something like this between these two. Okay. Therefore, the temperature will be of the form T is equal to T prime times Z. There will be a linear variation of the temperature, okay, which is equal to T prime times R times cos theta, okay, which is equal to T prime times R P1 of cos theta. Okay. So, this term that increases proportional to R basically corresponds to a source and a sink that are separated by a very large distance, and you are looking at the temperature somewhere in between. Okay. So, that is in a sense the inverse of this other problem where I have a source and a sink which are separated by a small distance and you are looking far from. Okay. So, those are the physical interpretations of the growing and the decaying harmonics. Okay. So, this is for n is equal to 0 and for m is for n is equal to 1 and for m is equal to 0, a dipole solution with the dipole moment, that is this distance L, aligned along the z axis. Okay. What about for, as I told you, right, in this expansion m can go from minus n to plus n. So, m can be minus 1, 0, plus 1. Therefore, there are 3 solutions. What do the other 2 solutions mean? Okay. I will not go into the details, but the other 2 solutions are basically dipoles that are aligned along the x axis with plus q and minus q along the x axis. Okay, that is for m is equal to 1, and m is equal to minus 1 corresponds to a source along the plus y axis and a sink along the minus y axis. Okay. In each of these cases, the dipole moment is aligned differently. The 3 solutions for m is equal to minus 1, 0 and plus 1, for 0 it corresponds to an alignment of the dipole, the source and the sink, the separation between those two, alignment of that separation along the z axis. The other 2 are for the separation along the x and y axis. Any dipole, okay, with separation in any direction can be expressed as the linear combination of these 3, because any vector can be expressed as the linear combination of the basis vectors. In this case, they are in the x, y and z direction. So, any dipole can be expressed as the combination of these 3. Okay. So, that is why you have 3 solutions, m is equal to 0, m is equal to minus 1 and m is equal to plus 1, with the dipole moments aligned along the 3 coordinate directions. Okay. I am sorry, I should write the with the 3 dipole moments along aligned along the 3 coordinate directions. Okay. So, those are the 3 solutions for n is equal to 1, m is equal to minus 1, 0 and plus 1. These are all dipoles, combination of a source and a sink of equal magnitude in such a way that the net source is 0. Okay. What is left behind when the net source is 0 is a dipole for which the temperature field decreases proportional to 1 over r square. Since the net source is 0, there is no contribution which decreases proportional to 1 over r. The next higher term is actually a contribution that decreases proportional to 1 over r square. Those are the decaying harmonics. The growing harmonics, on the other hand, are constant, okay, temperature gradient solutions. Okay. So, for n is equal to 0, it is aligned along the z direction. Okay. For n is equal to 1, okay, I will have an alignment along the x direction. Okay. Sorry. Okay. So, if I take this as the z, this as the x and this as the y, okay, separation between these two surfaces is much larger than the volume that you are considering. Okay. That is the inverse of the problem of point sources. Okay. And n is equal to minus 1 corresponds to separation along the y axis and n is equal to plus 1 along the x axis. So, these are the 3 linearly independent solutions. Okay. For n is equal to 1, all of these decay as 1 over r square for the decaying harmonics. They increase proportional to r for the growing harmonics along the 3 different coordinate directions. The next solutions, okay, the next solutions for n is equal to 2, okay, the temperature is given by, okay, A2 r square plus B2 by r cubed, okay, into y2m of theta and phi. In this case, m goes from -2, -1, 0, +1, +2. Okay. I will not be able to go through the details of how to derive these. The procedure is exactly the same as I had done it for the dipoles. Okay. What do these correspond to? Okay. Okay. The growing harmonics, okay, the growing harmonics correspond to two sources and two sinks, okay, of equal strength. Okay. So, the first one corresponds to a dipole which is aligned in this direction, the next one corresponds to a dipole that is aligned in the opposite direction. The net source is 0 because the source and sink strengths are equal. The net dipole is 0 because the dipole moments for the top one are exactly the opposite of the dipole moments of the bottom one. Okay. What you are left with is what is called a quadrupole field. Okay. Okay. I told you that the dipole decays as 1 over r cubed. If the net dipole is 0, the next higher order term has to decay as 1 over r cubed. Okay. The dipole decays as 1 over r square, source decays as 1 over r, dipole decays as 1 over r square. The next higher term has to decay as 1 over r cubed. Okay. So, you get this by a combination of two sources and two sinks in such a way that the net source is 0, the net dipole is 0. Okay. And what you are left with is a quadrupole field which basically goes as, okay, this is for, okay, n is equal to 2 and m is equal to 0. Okay. In that case, we get something that goes as, okay, B2 by r cubed, okay, P2 0 of cos theta. Okay. So, that is for m is equal to 0 where you have axisymmetry along the z axis. Okay. You can get it for other values of m, okay, -2, -1, +1, +2. I will try to explain to you what these physically represent. Okay. These are, okay, of the form. Okay. The first one is along the x y plane. Okay. You have two sources and two sinks along the x y plane. Okay. The net source is 0, the net dipole is 0. Okay. So, this is called P x y. Okay. Okay. Then you have one along the y z plane. Okay. I am taking projections of this. Okay. So, y z. Okay. In this, once again you have two sources and two sinks. Okay. And then you have one along x z. I am sorry, I made a mistake here. So, this is one solution for m is equal to 0. Okay. Then you have 3 solutions in which these sources and sinks are separated along the coordinate axis, x and y axis first, y and z axis next, and x and z axis next. And finally, you have one final solution in which these are off center along the x y. Okay. So, this will be off axis. Okay. So, these are called x y, y z, x z. Okay. This goes by the name of x square minus y square, and this is z square. Okay. These are the fundamental modes in the spherical harmonic expansion. Quadrupole, all of them combinations of 2 sources and 2 sinks in such a way that the net source is 0 and the net dipole is 0. There are 5 fundamental solutions of these, one of which is axisymmetric about the z axis. The others are all in the x y, x z or y z planes. Okay. These decrease all as 1 over r cubed. Okay. And the next higher term will decrease as 1 over r to the 4ths, that will have 4 sources and 4 sinks in such a way that the net source, net dipole and net quadrupole are all 0. So, by a combination of these point sources, just single point source gives us n is equal to 0, one source and one sink, a dipole, gives us n is equal to 1, 2 sources and 2 sinks gives us a quadrupole, and so on. So, these are identical to what we got by looking at the heat conduction equation with a delta function source. Okay. The two are identical. You can have a 1-to-1 correlation between the solutions for the delta functions, the sources and sinks, and the Legendre polynomial expansions. Since all of these are all orthogonal to each other, any temperature field due to any source can be expressed as a linear combination of these. That is precisely what we did when we solved the problem for the heat conduction in a composite material. We expressed it in Legendre polynomial expansions. Since each of these terms is orthogonal to every other term, okay, any solution can be expressed in terms of these. And just from the symmetries, you can construct a solution for the Legendre polynomial expansion, okay, for the heat conduction equation with inhomogeneous terms. I showed you how to superpose delta functions and how to incorporate boundary conditions. With this, we will complete our discussion of the diffusion equation. Okay, I had shown you how to solve it in multiple ways. One, by separation of variables in Cartesian coordinate system, spherical coordinate system. Second, by thinking of an inhomogeneous term which is in the form of a delta function and then generalizing it to a distributed source of energy, along with boundary conditions which can be satisfied using symmetry arguments. Next lecture, we will start the opposite limit, convection dominated flows, where the Peclet number is large, okay, the opposite of the present case. Here the Peclet number was small, so we neglected all the convection terms. In that case, the Peclet number is large, and you would think that you can just neglect the diffusion terms. However, transport to surfaces has to take place ultimately due to diffusion, because convection is only parallel to the surface. There is no velocity perpendicular to the surface. How do we solve those problems? They are all solved using boundary layer theory, using similarity solutions that we had seen earlier. I will start convection dominated transport in the next lecture, and I will see you then.